Hey everyone! Welcome back to yet another episode of the GattoCast. Dear human beings listening to this podcast for the first time, well, I hope you enjoy your time with me. And tonight I'm going to talk again about astronomy and astrophysics. So, tonight's episode is going to be another one for the series of Explaining the Universe to Joey de Maio. So for those of you who missed the first episode, let me just check because I'm hearing some strange noise. I hope you can hear well. But anyway, um, let me have some feedback if you can listen to my voice as you should, like clear and loud. So thanks a lot for joining me. Last time we had a chat about languages, and tonight I'm going to talk about another topic that I deeply like and appreciate, and it's also the topic that happens to be my full-time job. Um, Again, this is astronomy, and so if you remember, the first time we had a sort of discussion, I was talking about astronomy, astrophysics, and cosmology in general. So I hope you remember that. I hope you didn't forget all the things that I was discussing back then. But just in case you did forget, let me go through again to the subjects that I was dealing with last time. And so let me do a quick recap on the previous episode. So if you remember, I was talking about the how you do cosmology in practice, and it turns out that cosmology largely relies on computational resources. So nowadays, when you're talking about cosmology, there's a lot of background that involves computation. So it's involving simulations and supercomputers. Like what I'm showing here in these pictures is the Barcelona Supercomputing Center, just to have you an idea of how these things look like and how the workplace, so the things that we astrophysicists have to interact with, look like. And so this is just a glimpse, it's just a picture on this supercomputing center. So last time I was discussing about how the simulations, so how theoretical ideas and then all the numerical computation that stand behind them, that can help us, like understanding things about the universe. And this is the theoretical part of cosmology. Of course, then all the ideas and all the theories that you have in astrophysics need to be tested against the data, against the observations. And for tonight, what I want to talk about is how to measure distances, because there's a very I think we cosmologists, but people in general, take things for granted. So that it's something that we can do sort of easily. We can measure how far away is a star, and we can understand why, when we say that the universe has a certain size, or that we say that the galaxy has a certain size, we sort of understand why we say that, and we sort of it's pretty. We don't even ask how do we know, like that the size of the Milky Way is around 24 kiloparsecs. So this is just to tell you that this comes from there's an interaction again between what is the theory, so what are the mathematical conceptions behind astronomy and cosmology, and then you need to carry computation. So usually you do this using the supercomputers, because the equations and all the ideas and all the mathematical ideas that stand behind these theories, that are the foundations of these theories, are pretty complicated to just solve by hand. And then the next step is, of course, to compare everything with observation. So this is more or less the structure. So you have a purely theoretical phase, where people think in mathematical concepts, abstract concepts about the universe and about the laws of the universe. You got a numerical phase where you try to write down these equations in a in some kind of computer language. so that you can solve the equations in an automatic manner, so you can automatize the whole process. And then third thing is that you need to confirm, sort of, you need to check these equations and these results with the observations. So again, this slide is just about supercomputers and simulations, and it's not very interesting except for the fact that you can sort of see what kind of computational power we need to deal with when we do this kind of computations. And then when you do these kind of simulations, one of the most striking results that we got in the last 20 years, actually this is a result from 1998, but it was confirmed during the last 20 years, is that if you look at the content of energy in the universe, so you want to look how much is there of different kinds of matter. So it's like when you talk about the human body and you say it's 60% water, then it's I don't know, it's other components. But in a similar way, then you are approaching the universe and you want to understand what kind of things are there that make up the full energy content of the universe. I'm talking about energy because energy and mass, by Einstein's formula, E equals mc squared, are usually dealt with as the same thing. So in terms of units, you can consider them basically the same thing. It's what we do in theoretical physics. And it turns out then that if you look at the universe and you do the computations and you look at all the you try to make sense of what your theory is of the universe, or of the mathematics that stands behind the description of the universe, you have these three components that make up the full distribution, the energy distribution of the universe. That is dark energy, dark matter, and normal matter. And so whereas normal matter is actually what we see, so it's like this glass of what is this, like Amaro, or whatever. It's like gas, the air that you breathe is the water that you see, any kind of matter that you can interact with. Dark matter and dark energy are two completely different things, and I'm not going to talk about in this episode, but just to tell you that if you remember, how do we get to the idea that there are unknown components in the universe? Well, it's not easy, but again, it's sort of it's an easy guess in the sense that you have a phenomena that you need to explain. And last time I was making this example of the car. So you see two lights in the night like this, and then your guess is there is a car behind these lights. Like this, if you see these lights moving, then you don't see the actual car, you just see the lights moving, right? So you know that there is something moving these lights. You cannot just move them by themselves. So and then by the noise that you hear, you might guess what kind of car is over there, and so on and so forth. So again, this is a deduction issue in the sense that you only see a part of what you are theorizing is there, but you have good reasons to believe that there is something behind. And again, like the point with the dark matter and dark energy, just like with the car, is that if you only see these lights, then we might end up with any kind of car. It can be anything you like if you just see the light and you don't see the actual car moving them. So there are several kinds of vehicles that might explain this, and unless you go there and put look at it closely with your eyes, then you would not be unable to understand what is there behind. And with the universe, it's pretty much the same thing. We see some effects, and it's mostly these kind of effects are mostly related to the movement of stars, for example, to the motion of the stars in the galaxy, to the motion of galaxies within clusters of galaxies. So you have galaxies. Most of the times they don't really live on their own, but they have like companions, and so they form groups. And so by the dynamics of these galaxies within these groups of galaxies, again, you can understand what is there, what is the what is the component, that there's some hidden component you don't see, but it's still it's there because it's reflecting its presence through the motion of these galaxies, through the motion of the stars and these objects. So let me just okay, I have a question here, and they're asking, isn't this the aren't these percentages changing since the universe expands? Actually, yes, the share of matter is within the universe is changing at each step, in the sense that at very early ages there was basically no dark energy, and the universe was dark matter and normal matter dominated. And so as soon as the universe starts expanding, then the matter is becoming rare, and then you have less of that matter, but it's being compensated by the dark energy. Again, I'm not going into details of the of why is this the case, how does dark energy work, and so on and so forth. It's another, it deserves a full episode on its own. But I think we, at least with this series of explaining the universe to Joey de Maio, I want to sort of build up the kind of knowledge that you need in order to understand how, at least do we why do we believe that these things are part of the universe, and so what are the actual observations that lead us to these conclusions. All right, so that was a part of the of the first of the previous episode. And today's episodes, actually, I want to talk about orders of magnitude and large scale structures. So I think it's pretty common when people are not really in the business of cosmology, um, of sort of not really having a grasp on really understanding what we are talking of when we are talking about planets, when we are talking about stars, when we're talking about galaxies and clusters of galaxies. So what are exactly these objects? How large are they? Are they, the why do we always refer to these structures? And so before I move on, let me answer another question, which is pretty interesting. And they are asking, Daniela is asking, is the Big Bang theory the only theory that is widely accepted among cosmologists? Actually, yes, in the sense that it is the most widely accepted theory, for a simple reason that we see that the universe is expanding. And so if it's expanding right now, if you do the trajectory backwards, you sort of guess that it should have been like everything compressed in a very tiny place. You just do the backwards equations, and this is roughly the idea that is there behind. Now there are other evidences for this, in the sense that the Big Bang theory was sort of formulated during the 50s. There was this paper by I think maybe before that, but anyway, there were some studies. I think one of the first one was during the 50s that theorized that there should be a cosmological radiation background. And so until the 50s and the 60s, during the 50s, there were two different kinds of theories competing. One of them was the Big Bang, and the other one was the steady state. Steady state theory was a theory by which the universe was sort of homogeneous and isotropic, which is one of the principles of modern cosmology, but not just in space, also in time. So the universe, no matter at which time you would watch at it, would look exactly the same. And how was this achieved? Well, basically, they computed that in order to keep a steady flow of matter, so let's say that you have the universe is expanding and it's going into, it's just expanding. Let me just put it this way. You have a continuous influx of matter coming from, it's just being generated out of nowhere. But they calculated this out of nowhere was actually extremely small. So you don't need so much to explain that. Though it sounds like sort of extreme idea, and that like to create matter out of nowhere, out of the void. Actually, there might be some kind of quantum theories that could, some extension of quantum theories that accommodate for that. I'm not really an expert on this, but actually the whole issue was sort of settled against the steady state theory during the 60s and the end of the 60s and the 70s, when they found out the cosmic microwave background. So they actually found out some kind of remnants of the light of the Big Bang. So you can actually see it in the sky. It's very hard to, of course, to detect, but it's a signal that you can measure, and it's It's the light that is coming still from the, from the initial flash. So that's that's what sort of ruled out other theories competing to the Big Bang theory. Now, within what we call the Big Bang theory, actually, this is like, no one in cosmology refers to the Big Bang theory as Big Bang theory. Actually, we call it the cosmological standard model. And this is, of course, part of it is the Big Bang, and that there are other parts of the theory, in the sense that it's a very complex model. And there are, of course, different aspects of the history of the universe that need to be explained. And so, for example, you need to explain the very fast acceleration of the universe right after the Big Bang, and that's the inflation theory. Again, it's just a part of the whole model. So the whole model is like it's like a set. It's like an ensemble of different subsets of different theories that explain certain aspects, and then you put them all together, and then you get the whole picture of the universe, right? So that's the I don't want to go, deviate too much from the tonight's topic, but that's very interesting as well. There's one of the interesting thing about science in general, and cosmology at the moment, is that there's many unknowns, and especially the fact that, as you see here, when I'm talking about dark matter and dark energy, actually you see that 95% of the universe is made up of stuff that we don't understand, which means there's still a lot of to look for and search for and investigate, provided this picture, of course, that this kind of picture, so these numbers depend on the theoretical assumptions that we make, and of course on the observation. Now, there might be changes in the observations in the future. We might come with to better observation or different observation of different phenomena, and change our view of the universe. Again, this is like the most it's like the most widely accepted picture, because it's the one that can explain the largest number of phenomena at the same time, right? So this is the thing that you need to gauge. So you have one theory, one model, and then you need to explain, for example, why is the density of galaxies that we see the one that we see? Why is there in the universe this number of galaxy, this number density of galaxy, and not another one? Why are galaxies this massive? Why do we have this many galaxies with this shape? Why do we have I don't know, this many clusters of galaxies? Why do we see this many clusters of galaxies with these shapes? So there's a lot of things that you need to explain. So once you have a theory, you need to account for a lot of phenomena, and it's not easy, of course. Like, it's not like writing. Anyone can come up with this model, sort of, but it's very different. It's very difficult to find a theory that can explain these many different phenomena at the same time. It's like with the car. So you need to explain the lights, you need to explain the sound, you need to explain the vibration of the soil. You could still argue that it's some kind of different vehicle, but there's like 3-4 kind of proofs that point to the same direction. And the same thing is with cosmology. So we have a lot of different proofs that point to the same directions. All right. So this was just to make a short recap on what I was telling last time, and let me move on the ideas of orders of magnitude and large-scale structures. So the thing is that when we're talking about the universe, we're talking about all these structures and objects that live in space. But when we talk about space, it can be anything from Mars to, I don't know, the Virgo supercluster. And it's two completely different objects, and it's two completely different kind of science, in the sense that, for example, I know next to nothing about planets and planetology. I seriously have almost no idea about the specifics of Mars, of Venus, of the solar system. I have a very, very basic knowledge. because I focus for most of my career on the large scale structure of the universe, which means basically from galaxies and above. So I'm looking at very massive objects, very extended objects. I'm looking at very large region of the space, and I'm trying to make sense of that. That's more or less what I'm when I'm dealing with when I'm talking about large scale structures. And so let's just start from the beginning. So this is the Earth. Okay, so you see the Earth, and you might think it's large, it's small. Anyway, this is the Earth, and so what you need to do then is compare the Earth to its closest neighbors. So there is the other planets in the solar system, and including the Sun, which is a star. So you see the Earth here and the Sun. So the distance between the Earth and the Sun is around 8 light minutes, which means that it takes 8 minutes for the light from the Sun to reach the Earth. Okay, so light has a finite value. It takes time to travel. It's not instantaneous in the sense that though it looks like this on Earth, of course, but it's not like this. Light moves as a wave. It has a wave. It has this wave particle duality, and so it takes 8 minutes from a photon. So a photon is a light particle. It takes 8 minutes for a photon to leave the Sun and then get to the Earth. Okay, and so 8 minutes, and this is, I don't know, it's I don't know the number. It's a lot of kilometers. Let me put it this way: it's a lot of kilometers. Then you have the distance between the Earth and Mars. It's around 10. It varies with time, of course, because both planets are orbiting around the Sun. So you can sort of compute the average distance between the Earth and Mars, but which is, again, it's something like 10 light minutes, 11 light minutes, again, depending on the point, at the point of which the two are located, because again they are moving with different speeds, and so the distance is of course is not constant. And I'm talking just to let you know, again, I'm talking about minutes here, and you might have noticed it takes around 6 to 9 months to get for a spaceship from the Earth to reach Mars. So it's 9 months for a trip which takes 10 minutes at light speed. Okay, so this is the solar system. Okay, sorry, I need to comment on Uranus here. It's very far away. I think it was around 3 hours, 3 light hours distance from the Earth. So it takes 3 hours, for me to look at Uranus. And sorry, I needed to say this, but it's and I wasn't even convinced about this. But anyway, let me move on with these scales, and let me talk about the Milky Way galaxy. So the Milky Way galaxy is a disk galaxy. As you can see, there's a bulge. Let me talk a little bit about the structure. So you have at the center, you have a bulge, which is like a huge ball, very dense, with a lot of stars. And there's like, I think the bulge is around 10 to the 10 solar masses, which means there's like 10 billions of suns, more or less, just within this small region. And then what you have here, you see these spiral arms, and they form a disk, but you can see clearly that there are some overdensities. Okay, and we happen to be located on one of the spiral arms. All right, so what do I want to highlight here is that the distance actually from our position to the center of the Milky Way is around 8 kiloparsec, which is like 24,000 light years, which means that it takes 24,000 years for a light ray, for a photon particle, to leave the center of the galaxy and reach us. And so if you remember, so this is 24,000 years, okay? And so if you remember, before we were talking about 10 minutes, sort of 8 minutes to the sun. So it's 8 minutes to the sun, it's 24,000 years, give or take, to reach the center of the galaxy. And so it's a significant distance. it's something that we cannot really think. We cannot even think about reaching the center of the galaxy with some manned spacecraft, right? Um, Before I move on, I see I have a lot of questions, and let me answer to some of them before moving on. So again, let just okay. We go to the Milky Way now. I'll answer a couple of questions. First of all, why does conventional physics predict a cosmological constant that is too large? Uh, it's complicated. It has to do with the particle physics and it, it's it, let me put it this way. It has to do with the processes of particle physics that happen at a very high energy, and so there are some quantities that are related to these high energy processes of again particle physics. Just to make things clear, when I'm talking about particle physics, I'm talking about the experiments, for example, at LHC. I'm talking about the experiments on the very, 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 very small scales. So, like electron scales, like subatomic scales. It's like the structure, the inner structure of the atomic nuclei, electrons, and all these kind of things that happen on a very small scale. So, it's the complete opposite of cosmology. But the interesting thing is that you can learn a lot of things about cosmology by looking at things that happen on these very small scales. So one of these things, one of the predictions that come from um particle physics is that there is an energy constant at some point. Um, it's called. It should be like a 0 point energy of some quantum field. Just leave it like that. And this quantum field is associated to, if I'm not mistaken, to the strong force. But whatever force you take, even the weak or electromagnetic, you would end up with a very, very strong, very, very, very high constant. So the point is that when you study these small particles, just to I'm trying to make things clear because it's a complicated concept. But when you take these small particles, you get some prediction for a quantum field that is giving some kind of universal energy density, which is what we think dark energy is, by the way. Except this number that you get from particle physics is much larger than what you get from cosmology, and it's still not clear. There's like theories. There are people that are trying to make theories about understanding whether there's some kind of cancellation process that's going on. That's like two factors that compensate each other and leave like a very small quantity, and this small quantity is the kind of energy that you see on cosmological scales with dark energy. But this is like speculation, so it's not clear yet. um, all right, so this is to answer the first question. um, okay, why most of the orbits are in the same plane? Now, for planets, I think it has to do with the planetary formation theories, which I don't know. So I think, if I'm not mistaken, there should be like a protoplanetary disk, and so planets should form within this disk. And then you might have some processes like collisions or mergers that take away of the disk, take away from this disk other some of the objects, or you might have some perturbation from coming from external sources that move some of the planets away from that. But I think that's the reason why. But I'm sorry again, as I said, I don't know much about planets. So um, one solar year is when our solar system goes around the center of the galaxy. Am I right? So no, the solar year is when the Earth goes around the. That's one solar year. I don't know, but I don't know what you mean. I mean, because it takes a few hundreds of million years for the sun to rotate around the galaxy. So the sun is rotating all over the galaxy like this. It's not actually fixed on one of these arms, but it's moving throughout all these spiral arms. Okay. Um, Anyway, so this is, yeah, the rotation of the sun around the Milky Way galaxy takes a few hundreds of millions of years, but I'm not sure because I don't remember the numbers out of the top of my head, so it might be more. But the important thing to notice is that this, again, just to give you a little bit more information about the structure of the spiral arms of the Milky Way. Again, so you have this very dense bulge here, and the spiral arms actually are not fixed in the sense that the stars are moving throughout them in a way. They are called stationary waves. And the way you should think about stationary waves is like when you have, for example, you have a traffic light and you have the cars. And so you will always see like a very dense number of, quantity of cars at the traffic light, but then they will move. And then there will be new cars, and it will, again, the traffic light becomes red, and you find this very high density. And it's the same here. So you have that stars and particles are moving throughout these arms, but at some point they are compressed. There are these stationary waves that compress the matter along this direction, so along the directions of the arms. And so the Milky Way actually is now finds itself along one of these spiral arms at 8 kiloparsecs from the center, which is, again, 24,000 light years, more or less, and across the Milky Way. So again, this is the Milky Way galaxy. Milky Way galaxy, important things to remember is that it's this disk structure with the spiral arms. You have the center here, the bulge, and in total you have a few hundreds of billions of stars. So you have like hundreds of billions of stars that look like the sun on average. You got all kind of different stars, of course, but when you measure stars, you use the solar mass as a unit. So you end up with counting around a few hundreds of, close to 100 actually, of solar masses in stars that belong to the Milky Way. And each one of these, not each one of these hundreds of billions of stars has a solar system just like the sun. It's less. And the other thing that is pretty important to notice is that not all of the parts that of the galaxies can host life, because, for example, these parts that are very close to the bulge, they are bombarded with a lot of cosmic rays. So the stars here, they emit a lot of energy, a lot of particles, and if you target one planet with too much energy, with too many particles, you will prevent the formation of molecules and will prevent the formation of life, basically. So there's a lot of parts which are sort of forbidden for life. They are disfavored. There's like a shell which is preferred in this sense, and the Earth happens to be in this shell. So we are lucky if we look at it backwards, in a way. So the next step in the local geography of the universe is the local galactic group. And so this is what I am studying during my I've been studying the local galactic group for many years from a theoretical point of view. And it's a very, very interesting object, because you see here there's the closest galaxy to the Milky Way. It's Andromeda, and it's placed at 700 megaparsec, which is like 2 millions of light years. Again, it means that it takes 2 million years measured on Earth for the light of the Milky Way to reach Andromeda. But you have a lot of other objects here. You have a lot of small galaxies. These are called dwarf galaxies. And these dwarf galaxies sometimes they can be like 100 to 1,000 times smaller than the Milky Way. And there are these large and small Magellanic Clouds, for example, that you can see in the southern sky. If I'm not mistaken, I think you can see them with the naked eye, and they look like nebulae. And they are actually two of the closest dwarf companions of the Milky Way. So these are two galaxies that actually the Large Magellanic Cloud is like the largest satellite of the Milky Way. Is located around 50 kiloparsec from the center of the Milky Way galaxy, which is twice the radius. And it's so this is actually 150,000 light years distance. So again, from the Milky Way, it takes 100. From the center of the Milky Way, it takes 150,000 light years to reach the Large Magellanic Cloud, which is one of these dwarf galaxies. So again, you try to remember this, that this local galactic group is called the group of galaxy because all the objects here are bound gravitationally. Okay? What does this mean? Is that you have gravity acting. So gravity is a positive force. It always adds up. And so on the one hand, you have this gravitational force between all these galaxies that is keeping them glued together. You have some inner motion. And on the other hand, you have the expansion of the universe. So you have these two counteracting forces. Like there's the expansion of the universe on the one way, and the other way is the gravity. This is called the group because gravity is dominating. So the mass of these two galaxies is keeping the whole thing together. It's like keeping the whole system stuck together. So it's keeping it united. And you see there's there's a lot of dwarf galaxies, and there's a lot of empty space in between. Now, one for one of the projects that I've been working on in the last few years is actually the how do you say, like the hunting for dark matter in the local galactic group. So I was doing mostly trying to reconstruct the position of the dark matter within actually not just local galactic group, but on larger scales as well, for larger distances, but also here. So trying to see how the dark matter would be distributed within this within the local group. And so again, the distance here is around 2 million light years, which is a lot, but it's still not over yet, because the local galactic group is part of the Virgo supercluster. Now, first of all, what is a cluster? A cluster of galaxies is it's a cluster of galaxies, the word says. So it's a large amount of galaxies that are all gravitationally bound together. So you have thousands or tens of thousands. You can have, it depends on the kind of galaxy. I'm not sure if you can get to millions, but you can surely get, I think you can actually. So you can get up to millions of galaxies, maybe including also the very small dwarf galaxies that make up these large clusters. So a cluster of galaxies is basically the largest object you can get in the universe, which is sort of gravitationally bound, where gravity is still dominating over the expansion of the universe. Right? So the supercluster actually is not gravitationally bound, but is still, this is bound in a, you can find that it's connected through another kind of analysis, which is if you look at the velocities of these objects, you see that they're all directed in the same direction. They're all like moving sort of in the same flow. You can look at the velocities of these objects and see, then you reconstruct their velocity in the sky and see that they're all flowing sort of in the same direction, and which means that they're eventually, like ideally, they would be collapsing through the same point, which is not going to happen because of expansion, but still you might have some collapse and merger of galaxies on smaller scales. For example, in the local group, the Milky Way galaxy and Andromeda are approaching each other at a speed of 110 kilometers per second, which means that in a few giga years, the two galaxies will collide, and then some things will happen. It's as a part of the I didn't study this subject myself, but my collaboration did a lot of simulations on trying to understand how it's gonna happen and when it's gonna happen. And there's some variability on the kind of scenarios that you can encounter when these two galaxies are merging with each other. But the bottom line is that yes, these two objects are going to be just one object if you move farther enough away in time. So same thing with the Virgo supercluster. You see here there are two very large objects. It's this Fornax cluster and this Virgo cluster. And you see they're all sort of connected. There is this filament, it's a filament of matter that is connecting. You see there are some stars, some small galaxies scattered all around. There might be some gas. There is for sure, as far as I am concerned, there is a lot of dark matter that is connecting the two objects, which you can notice, you can detect it in sort of indirectly, again, through its gravitational effects. And then you see here that this is also stretching. There are all these Virgo groups that are also part of this supercluster of galaxies. So what kind of distances are we talking about here? The distance from the local galactic group to the Virgo cluster is around 60 megaparsec, which is, it's multiplied by 3, it's 48. So it's 48 million light years. So say 50 million light years to the center of the Virgo cluster. The Virgo cluster, by the way, is the nearest object to its largest cluster closer to the galactic group, so to the local galactic group. And again, it's 50 million years distant from our galaxy, which is quite a lot. So this is as far as the local supercluster geometry is concerned. But then you can move, and then you can look at the whole ensemble, at the whole zoo of local superclusters. So this is the Virgo supercluster. Here you got Hydra Centaurus supercluster. This is where is Coma supercluster. Here it's one of the most famous. It's 80 megaparsecs from us. It's one of the most well-studied clusters. There's a lot of observations on the properties of the Coma cluster, so it's one of those that when you do astrophysics you always encounter, because it's just so large, so massive, it's so large. You see it's stretched. There's many substructures within it, many subclusters, but and again, it's 80 megaparsec away from us, so it's like 250 million light years, and it's 5 times as far as the Virgo supercluster. So let me mention this. Is this Laniakea? I remember reading briefly about it. This is not exactly Laniakea. Laniakea is, I can talk about that because I still work nowadays with the guys that discovered the Laniakea. Laniakea is a supercluster, which I think it's made of this. It's like Centaurus, Hydra Centaurus, Virgo supercluster. There are other objects that belong to it. I'm not sure about Coma actually. I should know better, but the idea is that Laniakea is the largest not really bound, but it's the largest structure in the local universe, where you can, if you do this trick that I was telling you before, you can reconstruct the velocities of the objects. So you have all these galaxies scattered around, and you look at their velocities, and you see that they converge more or less to the same direction. Maybe I think it's useful if I just look for a picture of Laniakea, and so I can show you what I'm talking about, because it's that's it. Okay, let me share this with you. I think it's a fairly interesting object to look at. Because it is part actually of the what we call the local universe. Okay, so it's this one. Actually, it's not the whole thing. Laniakea supercluster. Like compared to what I was showing you before, there's a Centaurus cluster, Hydra, um, Virgo supercluster is over here. You see that Coma is not part of it. But the interesting question is how you determine this. I'm not sure you can see this actually. Let me see if you're, yeah, you are seeing that, right? Um, sorry. Oh, let me share this other picture with you because it's just better. Okay, so this is the Laniakea supercluster. It's a subset of what I was showing before. There's uh, again some of the clusters you were seeing in the previous picture were not part of it, but yeah, you see here the local group is the Virgo supercluster. It's over here, Centaurus. Where is Pavo Indus? Is there Perseus Pisces also? No. But the interesting thing about Laniakea is that, as I was saying before, generally you would identify objects thanks to gravitation. So you have to look at whether they are orbiting around some kind of center of mass. If they're bound, basically, if you see that gravitation is keeping them together. In this case, you are not looking at gravity. You are looking at velocity, and so I think this is okay. Let me share this. And what these people did, so it's my collaborators did before I joined the collaboration, is this. So we're looking at velocities. You see these lines. There are flow lines of velocity. It's like the trajectory of an object that is placed here. It would, like, ideally, if you were to put like an object here and just follow the velocity flux, it would move along these directions. Okay. And this base is called basin. It's like this circle that you see here is identifying all the objects that would move towards the center of this of this circle. It's not so clear maybe, but it is that all these whole lines. Yeah, I'm trying to. I cannot really make it bigger. I'm sorry. I didn't prepare it, so. But the idea is that these lines, you have to look at where the lines go, and then all the objects that move in the same directions, like to the same point, to the same center, according to these lines, then they belong to the same supercluster. In this case, it's called Laniakea. It's one of the objects that has been identified. And it's a very nice technique that can be used to identify these objects. It relies on, again, on the velocity of the galaxies, and it depends on, it relies on tracing the each galaxy's position and each galaxy's velocity, and then sort of trying to reconstruct using galaxies as tracers of the full velocity field, of the full flow of the universe in a way. And it's something that, like, my personal research is basically based on this. So I'm using, just to open a small parenthesis, but what I'm doing in my day-to-day life, I'm trying to use this kind of velocity fields that you can reconstruct in the universe to trace the dark matter. So to use these velocity fields as proofs for the distribution of dark matter. And so out of these maps that you see here, this is like a density map. It means it's like mapping on two dimensions. So you should imagine yourself to be like outside of the Earth and go very, very high in the sky, again, to quote myself, and then look at this matter, and you would see something like this if you were able to look at the gas and the whole kind of particle distribution. And yeah, then you would be able to see where the particles are moving and how these flows go. And then these flows, they also tell you a lot of information about dark matter, and this is what I'm working on at the moment, more or less. So sorry for this, but Laniakea, it's something that maybe I can make, if you're interested, I can make GattoCast episode just on Laniakea and talk a little bit more in depth about how do we study objects in the local universe, which is pretty exciting for me because it's my job. Anyway, let me go back to the to what I was actually showing before. Again, this is to understand what kind of structures you see in the universe, and to go back to Laniakea, what you would call Laniakea here is this something around like this size. So Centaurus was part of it, Pau Indus, Hydra, like this part, and then again you would see here these other superclusters. So there's lots of superclusters, and so last step. This is the observable universe, and again this is a small part of the observable universe. Observable universe is a very simple definition. It means just up to where we have been able to look in the universe. So these are the most remote galaxies that you can see. They are around 30 billion years old. What does this mean? Again, the idea is that light travels at a finite speed, and so an object that is located very far away from us while the universe is expanding, you have the light ray that is trying to reach you, and while the universe is expanding, and so there are many objects that you wouldn't be able to see, but there are those that are within the boundaries of this of the observable sphere. Then eventually, after 30 billion years, will get you you will get an image of them. And the cool thing about this is that when you look at these faraway galaxies, you are basically looking at galaxies how they look like a few hundreds of million years after the universe was formed. And so this is something you should know. The farther you look into the universe in space, the farther you're also looking in time. So you're looking basically at something, you're getting a picture from the past. And so you're getting a picture of how the universe looked like in the past. And this is very useful because, of course, when you want to elaborate theories on cosmology from the Big Bang to today, you need to test them at different stages. And it turns out that due to the finite speed of light, you can actually test theories and say, for example, my theory predicts that this class of galaxy forms 7 billion years after the Big Bang. Maybe you have another theory that says it's 5 billion years. And then you look at observations, and then you see, I don't know, a galaxy that forms at 4.5. And in this case, you would, like favor the second theory with respect to the first one that was predicting that no such thing would exist up to, 7 billion years. I hope I wasn't too... I hope it wasn't too complicated or too, contorto. I don't get the English word for that. But anyway, let me move on with the presentation. So this is, again, I'm telling you all the time, this object is this many billion years far away. This object is this many million years far away. So by the way, the size of the observable universe is 28 gigaparsec, which is 28 times 3. It's like make it 100 billion light years. So it takes hundreds of billions of light years to see it. Of course, the reason why you can see distant objects is that in the meanwhile, the universe got bigger. So because of expansion. So when the light was emitted, the universe had a different size. So, but again, all the time, I'm claiming that objects are this far away, and this galaxy is this many million years, this many million light years, far away, and so on and so forth. But how do you actually measure distances in the universe? So, like on the Earth, we know you take a ruler, you take a light ray, you measure time, you can move from one place to the other, the speed, and then you can compute the distance if you just keep track of time. But you cannot really go to a star and send some signal, or go there with a ruler and just measure by hand what's the distance of some objects from the Earth, from where we are located. Um, okay, so sorry, I forgot this thing. Before we move into the how do we measure things in the universe, I just wanted to show you this very nice picture that is taken from the Planck 2013 mission. And it's just a schematic sort of like easy way of looking at the universe. And it's a simplification in the sense that you have here, this is like take every slice, and every slice is like how the universe, you make a two-dimensional projection of the universe on these slices and just put them one after the other. And so this is how the universe looks like after 13.77 billion years. So from the Big Bang to today. This is sort of what we want to understand with cosmology. So we want to reconstruct this picture and the various phases of the history of the universe. And so you start with quantum fluctuations and the Big Bang. You have this inflation phase. I'll talk about maybe next time, but and then you see that you have several phases. You see like the shape and the colors, also like the density of the universe changes with time. At each step that you see here, each slice is different, and so eventually you end up today where you see these galaxies and these voids, and you end up with the theory of dark energy and accelerated expansion, which is it's pretty solid observational result, but still it's largely unexplained. So yeah, this is called dark ages. You see you have several phases. Dark ages is where you have the light cannot really travel freely because there's a lot of free gas, and the light is going, it's like basically all the time being absorbed by some molecule or some particles. So it cannot really travel, and so when light cannot travel, by definition, it's like you cannot see anything. There's everything that we see is mediated by photons, and so if you have a lot of particles, photons will be absorbed, and so you don't see anything. It's like basically saying that you have a very thick kind of wall of smoke where you don't see anything because light cannot go through. It's just being absorbed, and this is what happened at the phase of the universe. And then, well, then you of course at some point you start forming the first stars, and the first stars are parts of the first galaxies. Galaxies again, they start to merge later in time into clusters of galaxies, and then clusters of galaxies evolve, and like in each galaxy you need a couple of phases until you reach to the formation of planets and eventually life in all the millions of billions of galaxies that are out there. And yeah, so this is just to sum up everything and see things also in a way in where you can look at things in as they evolve through time. So this is one of the most used and abused pictures I've ever seen in my life, but it's very nice because it summarizes in one image the whole history of the universe, and it's a very powerful way of looking at it. By the way, let me go back to the main question of this podcast, which came 1 hour later, and I'm sorry for being so late. I hope you are not so bored, but this is the key question of tonight. How do you measure distances in the universe? So how do we know that objects are a certain distance from us? Because all the theories that we have in the universe, everything that we know about the universe is based on the assumption that we can measure the distance of a star, the distance of a galaxy, the distance of a cluster of galaxy. Because of course, when you know the distance, then you can reconstruct a map, and you can put, as you've seen before, you can put all these objects, all these stars in place. You can look at the structure, at the distributions, and their abundance, at their density. You can look at all the properties that you look at are related to the fact that at least we pretend to know, we think we know, that we can measure the distance. So we see, of course, when you see objects in the sky, they are on a two-dimensional surface. I mean, the sky is like, yeah, you cannot really see 3D. You just see lights. Maybe there are some fainter lights. But when you look at the sky, it's a two-dimensional projection. And out of that, you need to reconstruct a three-dimensional projection of the full matter distribution of the universe. And so it's pretty complicated, and there's many ways you can do that. And I will talk about three this time. I won't talk about the most important one because it requires a lot of information and a lot of previous talking about it. But let me just introduce the easiest ways we have to measure distances, at least of nearby objects. And the first one is the parallax. So parallax is pretty simple. You just take your finger, you put it in front of your nose, you close one eye, you close the other, you see the finger is moving, right? And the farther away, the less it is moving. And this is what you see here. It's a picture of the Earth orbiting around the sun and looking at the same star. Now imagine that you have a star here placed exactly above the sun, and you look at it when you are, on the two at two, opposite sides of the elliptical orbit around the sun. And so you look at this, you're looking at the same star. What happens is that by the same effect that you have when you look at your finger and you close your eye, that the star, the apparent position of the star will be located somewhere else in the sky. So in this case, when you're here at this extreme right position, you will look at it and it will appear here, so on the left. Opposite things happens when the Earth is located here, so on the extreme left. Then you will have an apparent position in the sky on the left side. Sorry, on the right side. And so the way that you can measure the distance to this star, it's actually measuring this angle here. So how much is this star shifted in the sky? So if you look at the sky, you see these background stars that are stars so far away that they don't move when you do this trick, but nearby stars, nearby objects, they do move. Apparently, of course, in the sky, they look at different positions because we are looking at them from a different perspective. And by looking at how much this thing deviates, then we can reconstruct its position. And this is fair enough. It's good. It works fine for stars that are reasonably close to us. But again, there are stars that are so far away. Again, it's like if you put your finger at 1 kilometer distance, if you close one eye or the other, you don't notice any difference. And so there are stars that are so far away that you cannot really use this trick to measure the distance. What do you do then? There is a general idea that stands behind most of the concepts in cosmology, and especially in this kind of measurements. And it's called the idea of it's the concept of a standard candle. So why standard candle? A standard candle is like a standard source of light. It's like a source of light that you know what its intrinsic power. So it's like, again, assume you have a candle and you know the luminosity of this candle when it's like 1 meter away from you. Then when you put this candle 3 meters away from you, you can reconstruct from the dimming of the light, because of course the farther you put it, the more dispersion there is along the path, and the dimmer the light source looks like. And so by knowing what's the actual intrinsic luminosity of the object, you can reconstruct its distance once you put this very same object at a farther away distance. So the trick is that you should find a standard candle, so sources of light that are, first of all, powerful enough that you can, like look at them, even you can recognize them even when they're pretty far away. And the other thing is that they need to be very, very, very homogeneous. Okay? So you need to have some kind of very stable and very reliable source of light scattered throughout the universe, so that, for example, I know that this kind of star in the Milky Way has this intrinsic magnitude, this intrinsic luminosity, and then when I see the same star, exactly the same kind of star on Andromeda, for example, then I can reconstruct the distance to Andromeda, because I know that these stars that belong to the Andromeda system are the same that are in the Milky Way, are the same that are in the Milky Way, and therefore I can reconstruct by the dimming, by the attenuation of light, I can understand how far away is Andromeda from us. There is one very nice class of stars that complies with this sort of requisite, and they're called the Cepheid stars. So they're called Cepheid variable stars. And what's the trick here? They are variable stars, so they're pulsating. There is a mechanism which has to do with the way with helium, with the way helium conducts energy and heat and light. So you basically, what happens in this kind of stars is that you have a core which is producing it's going through nuclear fusion reactions, and there's it's like the engine of the star, right? So you have this engine that is heating the helium around it. So what happens that when you heat all the gas around the star, the gas is it gets a lower density. Okay, so it gets hotter, then it gets a lower density. When it gets to a critical lower density, it starts to cool again. So you are heating it up to the point that it's so now it's not dense anymore, so it starts getting cold and it starts collapsing again. So it's going through this cycle all the time. It's like expanding and then collapsing, expanding, collapsing, and it's very regular. So there are stars, again, these are called Cepheid variable stars, that go through this cycle of, you see here on this first plot on the top left axis, it's luminosity versus time. So the luminosity is going up, then it's going down, it's going up, it's going down, it's going up, it's going down, with this cycle of expansion and contraction of the star. And these cycles are very regular, right? So you know that if a star has a cycle of 3 days, it has this kind of luminosity. Okay, so what you see here in the other plot, you can relate in a very precise manner the period of this cycle, so the distance that is there between the two peaks of the luminosity, and the luminosity in itself. So you can look at stars that are very far away. You can look at, the what actually you can do. It's something like this, right? So this is an actual example. You look at the star, you see now it's dimmer, brighter. So it's now, this picture is not so good, but the idea is that you actually find this kind of stars in other galaxies that have this cycle of dimming and getting brighter. So and again, you know that there is this relation between the luminosity and the period. And so once you know the period, so you can always look at the sky at some part of the sky and search for these kind of stars. And once you see one, you point your telescope to that direction for a month or two, whatever. What's the time that you need to get a reliable measure, and then you can reconstruct this cycle. And once you have this cycle reconstructed, you can also extrapolate the luminosity. So again, you go here, you see that from April to May it takes 1 month to get back to the initial position. It means this is somewhere around here. Number of 31 days is associated with the luminosity that is 10 to the 4. And so now 10 to the 4 solar luminosities, it means it's like 10 times to the 4, so it's 10,000 times more luminous than the sun. Now we know how luminous is the sun. We know very well how far away is the sun. We can send probes to the sun. We can do a lot of things with the sun. And so now we look at the light here, we know, oh, look, there is this kind of attenuation of the light from this point in space to us. Now we can reconstruct the distance from this point to the Earth. And this is another of the ways that you can reconstruct the distances. But again, this relies on the fact that you can look at the star and make a reasonable measurement of the of this cycle of dimming and increasing in brightness. What happens when the star is so far away that you cannot really measure these kind of objects? You really need to look for extremely luminous objects. And it turns out that in the universe there is one kind of objects, that is supernovae, that are the most extremely luminous objects in the universe. What does this mean? Is that a supernova is basically a phase of certain stars that certain stars go through when they explode. So supernova is like it's the explosion phase of a star. Now, stars may explode in very different ways because they tend to explode when they are above a certain mass. And so if you can above a certain mass, it means it can be 10 times that limit, or it can be 5 times. It can be just slightly above the threshold, and so on and so forth. But it turns out that there is a very regular kind of supernova, kind of exploding stars. And this kind of supernovas are called type 1a supernovae. And it's a very interesting system. It's a very interesting way of looking at the universe, because, again, since these kind of supernovae are very regular, they're sort of everywhere in the universe, you can use them to measure distances for up to a very, very far away scale. So what's going on here? Let me explain this picture briefly. So this type 1a supernova is actually a system of stars. You have white dwarf star here on the left. So it's one kind of star which is very small and very cold, in the sense that it's not really burning hydrogen anymore, as usual stars do. Whereas on the other side, you have another kind of star. Usually it can be a blue star or a giant red dwarf. Sorry, a giant red star. And the thing that is going on here is the following. This is why this mechanism works, is that the star here is losing mass. It's like it's being sucked away particles from the white dwarf on the left. So this white dwarf is basically stealing mass from the companion, and it's increasing its mass. And what happens is that when you increase your mass for this kind of white dwarf stars, you reach a limit which is called the Chandrasekhar limit, in which you will have so much mass in the star that you're actually starting, like, the own gravity of the star will start to make additional fusion reaction. There will be additional nuclear fusion reactions that will make the star explode. So basically what's happening is that there will be so much pressure, so much compression coming to the star from the outer layers that have been absorbed by this from the companion, that eventually at some point, when the star has stolen enough mass from the companion, it will explode, just because this amount of mass means that you will have this amount of pressure. And when you have this amount of, like, a given amount of pressure, you will start another chain of nuclear reaction that will make the star blow everywhere, like this. And so what's interesting about this is that the way the star explodes is very regular. what you see here, it's the light curve as a function of time. What is this? It's that the explosion has several phases. And so maybe the easiest thing is just to show a video on this before coming back to let me share this. Can you see this? Okay, let me just wait. All right. So this is what happens. You see there's a red star that is losing mass slowly to the white dwarf, and you see the mass of the white dwarf is increasing. It's increasing. This is the limit. It's 1.45 solar masses, which means that when the star gets to 1.44 solar masses, it explodes. And you have seen there was, now let me go back to the main slides. But you've seen that, let me show again, the explosion phase, which is, so again, you see that it's increasing the mass, then it's getting closer to the Chandrasekhar limit, it's 1.44 solar masses. And you see the explosion is, there's a light that is going up and there's going down, the light curve. So the intensity is increasing and then decreasing. Now, what is interesting here with this phenomenon of increase and decrease, let me stop sharing and share another screen, is that it's very regular. So the actual So this phenomenon of explosion is very regular in the sense that the time that is passing between the starting of the start of the explosion and the peak of the luminosity is basically always the same. It's always the same. And so the shape of this curve is always the same, which means that when you see an explosion in the sky and you see this kind of shape of the light curve, of course, the intensity will be different, because if you place the same source at a larger distance, you will see a smaller intensity. However, the shape of the curve will always be the same, approximately. And this is because this kind of explosion is triggered when the mass reaches 1.44 solar masses, which is the Chandrasekhar limit. And so again, this is why is this important? This is important because now we can use this kind of explosions, this kind of extremely luminous explosions, to measure the positions of objects at farther away distances than what we can do with the parallax, and that what we can do also with the Cepheid stars. So this is, again, this is called the cosmic distance ladder, in the sense that we are, for each kind of distance, like for any, there's sort of measures that you can use depending on the kind of distance that you need to measure. So if you want to measure objects that are within a few light years, then you would use the parallax. With tens of light years, then again, tens to hundreds, you would use Cepheids, maybe up to, I think you can use that for Andromeda as well. So in that case, it would be like millions. But then when you're talking about supernova type 1a, you can probe the universe much deeper into, you can measure the position and the distance of objects that are much deeper than what you could actually do with the other techniques. And so I think I can end it here. I hope you could sort of understand everything. I hope I was clear enough, because I fell into a couple of problems when trying to explain things. It's not so easy I'm not so used to that. So thanks for being part of this while I'm trying to make myself sort of popular science presenter. But anyway, it was a pleasure having you here. Let me see if you have any more questions. And okay, let's just finish with this question. Do we have any other of these supernovas somewhere close? Not that I know of. The problem is that, so these objects, white dwarf stars, are very faint. So it's very hard to know in advance when you will be able to see one of these supernova, because again, they are faint, so they are used to probably very far away objects, and it becomes very luminous just when it explodes. And so usually what happens is that you have a network of satellites that are pointing to every direction in the sky, and as soon as some of these of these telescopes finds a supernova, then there are some telescopes that will try to measure it, like to measure this light curve. So they will. The important thing is, again, is to measure the way the light is going up and then down through all the phases of the explosion. And so this is the most important thing, because again, the more when you have a large number of these objects, you can make statistical samples out of it, and you can study a lot of properties, not just about the distances, but you can learn a lot about the universe itself and about the way the universe expands. And I think I'm going to talk about this in one of the future GattoCast episodes. And so thanks again for being with me. I hope to see you all at the next GattoCast episode. See you in the future.